You might have to that's fine. Or stone. Okay. If you want to put in your already done that.
Okay.
Oh wait, it should be
So just getting started.
why isn't it displaying it? Wrong. I don't see Shriya slides in here. So all of Ali's really is. Okay. Do we have to change the thing? I should plug it in. Yeah. Like I can. Stuff. Why I actually like plug into anything? Yeah, this is what's the remote?
Learn else. Wait. I mean, she's gonna come back like in a minute. Should we just start at one? Do you want to start at one? Because I also don't want to like rush things.
I don't want to start out. So I don't know why. Because I have to study for it. I don't want to not know the quiz today. So it's huh?
Maybe. Wait. What was she
Can I
supposed to
go?
cover?
Can you double check this?
Should be in this quiz.
I'll work on this.
It's odd.
And it said when,
I'll take it.
yeah.
Information.
Yeah.
Was she not in the channel? I thought she was.
Yeah. I don't think I joined you.
Huh?
I think you joined this.
Okay, is the laptop sending the input to the projector?
I believe so. I just plugged it in. I haven't checked.
Oh, shit, I didn't mean to do
You
that.
could do.
I meant to hit,
Alright.
yes. That's what I wanted to have. It's sending a signal out.
We're actually tutors for Oh,
No, I know. I'm trying to project play nice. Better recording. Okay, give me a second. I may just have to manually just jack into it. We have the same problem we had with the other one. Okay, give me a second. What?
You don't need the last state, but the rest of the last state is.
So the I is not needed for last state?
No, state 1 1 0 0. You don't need it. You just get rid of it in general. Someone go ahead.
Okay.
Yeah.
Yes.
Yes. You sent you the Twilight. I thought. Oh, yeah, we're all in love, I guess. I was like, so where is this going? Where is this going? She's not in it.
Devices will work crap.
Okay, so for if I can write those or
Yeah. Because my it's such a weak pianist. Like they're like bare bones.
yeah, so
Sure, yeah. Give us your. Worst case is the other one.
Yeah, that's my thought.
Here.
There we go.
Oh, thanks. Thank you.
Very well. Sorry, not my comfortable to use right now.
Yeah. Sure. Really? That's all.
Thanks. I think you guys are ready to go.
Okay. Uh, can y'all still see me? Alright, it's not see me. Can y'all still hear me? And whoever is in the meeting. Or shoot, meeting. I don't know what's true. So I think I probably, can y'all hear me? Whoever is in the teams. Uh, Okay, so this is the test to review for 2010. My name is Michelle. I'm gonna go over like the first like layer of material that's gonna be on the outside. If you want to do extra help, it will be in there, like throughout the if it's not me or anyone else is presenting today, it will be tutors who can work your 10. And there's also this meeting will be recorded, so if y'all need to go back and rewatch anything, it'll be on IEEE YouTube. So the first part of y'all's list is gonna be universal game conversions. So that's just like using a NAND to like in place of a not or and or. So the best practice for this part is purely just memorization. Just know that the difference. So y'all have to know NAND conversions and NOR conversions. The best practice is to just remember for OR on the for the OR gate on the NAND conversion, it's just going to be kind of like a flip on the NAND conversion for the best practice is just to practice like make up formulas, and this replace like a NOT gate with NOR. This is an example that I found on y'all's found on what's it called? Zybooks. So the equation Q equal to A not B or C and D. So we're given on the left hand side we see what it is as a pure equation form. And then we replace the not gate with what we've seen here. Sorry. Here. So there's like a first not, that was the A not. We're just replacing anything with the names, and then whatever is similar, if you can see here, there's two no nor representations. Sorry, not representations of man. We can cross them out if they're in like a series, and then you can simplify the equation to get this. Do y'all have questions on that? Okay, great. And then I just did the same equation but with more. Again, you're just replacing each like component with the respective NOR conversion and canceling out anything that's like common. So in this case, there's two not conversions of NOR, so I just cancel that out and then add a simplified equation. Next thing y'all get into is the muxes. So just know a mux is kind of like a switch, and depending on what the select lines are, you're gonna get a different output. So select lines are like n and select lines are equal to n, and then the number of inputs is 2 to the power of n. And as you can see in this example, oh yeah, and then another best practice for this one is going through like the guidebook simulations again. Those really kind of help uh, reinforce like the theoretical concept of it. But as you can see, since it's two select lines here are 1 and 1, we're going up to I3 and getting that as the output. And another practice you could do is, as you can see in I0, so that represents 0 as a decimal value. I1 represents 1, I2 represents 2, I3 is 3. So you just get the select lines would just be the binary. Next, we get into decoders. Decoders are the inputs are equal to n, and the outputs are equal to 2 to the power of n. Similar to a mux, they work kind of like the same. I wouldn't think of them as select lines, but we are basically just getting the So in this case, the input is 1 1. So you would go to the the highest like significance, which is Y3, and that would just be here, and you just forget about everything else. And again, if this was 1 0, it would just be 0, 1, and everything else is 0. Next, we get into encoders. Encoders are like the opposite, kind of like the opposite of decoders. You have more inputs than outputs, kind of like you're encrypting something. That would be the best way to think about it. So in this case, inputs would be to the power of n and outputs would be n. And it's the same thing but flipped. So when um, d0 is 1, d1. So when it's 1, 0, 0, 0, you would get the select line of 0. So that's kind of like the binary equivalent, d0. And then so forth with the other. And then if the parity encoder, I don't know if y'all like actually get into this, but I'll just go through it. So the parity encoder basically, um, it just outputs whatever is at the highest significance or highest priority. So in this case, if we go from the top, it's D0. So D0, 0 is just 0, 0. And then let's skip up to where we have two ones in the input. So when it's 0, 1, 0, 1, you would just take the priority would be D2. So you just have like the binary equivalent of that, which should just be 1, 1, 0. And then again, when you have uh 1, 0, 0, 1, 0, 1, 0, the highest priority would be the D3. So you'd have the binary equivalent of 3, which would be 1, 1. Y'all good on that? Okay. Then we have the half adder. Um, have y'all learned half adders? Twice. Yes, yes. Okay, cool. Okay. I would for this one, it's more of like do the homeworks again. That's like the best way to do this. Like conceptually, it could make sense, but once you do the homework, it's gonna like solidify what you're learning. Um, be sure to know the equations. So for C carry out would just be A and B because there's a one in that thing there, and then for the sum it would just be this A naught B or A B naught, and then this would be the circuit diagram. I have an example. Next one. So this is an example of like four half adders, and this is like an incrementer. Have y'all seen this in the homeworks? Yes. Okay. So y'all might have seen it in like a different way, but this is how I saw it on my test. But so you would have like different like values here. For example, it could just be 0, 1, 0, 1. So then you would take 1 and 1 plus 1, which would be 0, and then you take the carry out here. That goes into the next one. The carry out would be 1, and then next one would be 0, and 0 plus 1, sum would be 1, and then the carry out would be 0, and then you would have 1 here, and then 1 plus 0, 1, and then again the carry out would be 0, 0 plus 0, and it'd be 0 for sum here. With the full adder, you're adding on a carry in to signify whether you're adding or decrementing. I don't have an example of decrementing, but I can go over it. So with this one, so only addition to this is you have like the CN. Again, know these. You can either know these through like the K-maps or you can derive them from the truth table. Oh shoot, that's not mine. Let me get an example. So instead of, I'm gonna use this as an example for the full adder. So off to the side here, you would have like a CN. If it was a 1, you would add everything together. So let's just say for the A input, it's 0, 1, 0, 1. And then you have the addition of a CN, which is 1 here. So it'd be 1 plus 1 plus 1 here, and then the sum would be 1, carry out would be 0, carry out would be 1, going to here. And then, oh, we would also have to have like an input for B. So there'd be 3 inputs going into each box here, and then you're just adding them. Same practice, getting a sum, carry out, and you would have a different like line for B here. Does that kind of make sense? Yeah. And then for the decrementer, you would put a 0 off to the side and for the C instead of can you help that here? Oh, never mind. For the C, and it would be a 0 off to the side, and then you would do the same thing with that. Do you have any questions on that? No? Any questions on anything I went over? Yes, Judge.
I'm gonna send a recording in tomorrow, going over, I think, binary multiplication and 2 other topics. Let me figure out exactly.
Do you want to go over earlier stuff?
Okay, I think you can go over your topics. I'm gonna record, send a second recording tomorrow that covers information sets, representation numbers, and binary multiplication and fractions in binary. It'll be like a short recording, and I'll like go through the whole procedures and how to solve those steps. Like, okay, just be on the lookout for that.
Is there like a laser or something?
Sorry.
Like a laser or something?
I don't think so.
Because I have some examples. Okay, so I'm going to talk about the fixed point representation.
Just use
The mouse. Okay. Okay. So this is the one with the cube and the format that they give right there. So I have an example right here that we're trying to convert the 6.1875 decimal to that representation to 8.4. So what you gotta remember here is that the format of this, the n is the total number of the whole bits, the whole thing. So then the f it's the fraction, the numbers, the amount of bits that are going after the radix point, and m, that they don't usually use it, but still it's good to know. That can be found with just subtracting n minus f. So an example here in the picture that I have is, as we all know, you have to convert the 6 to binary. That we know how to do that, right? We divide by 2, and then we find a remainder, and we continue doing so until the quotient is 0 and the remainder is 1. And we go from the last one to the top, right? That's 110. And then to convert from the decimal to binary, we have to multiply, not divide. So we multiply by 2, and the result we again multiply by 2, and we go and go, and we have to multiply the decimal point. Like for example here, we will now multiply 1.5 times 2. We'll multiply 0.5 times 2, and that will be the one. So this is going from the top to the bottom, not the other way. That's a very important remark. And we go 0, 0, 1, 1, and that's what we have here. Here's a little picture for you guys to understand. If this method is not making that much sense to you, you can also just use the 2 to the negative 1, 2 to the negative 2. I think that's another way that you learn about it. Any questions about that before? Because that's like important. So okay. So now the algebraic representation, I think for the test, the only one you're going to use is the 32-bit, not the 64. It's also very good to know a bit of difference that you have. Basically, a more mantissa and then pick a couple more bits for the exponent. So this is basically the format: 1 point, the fraction bits, and 2 by the exponent. So in the IEEE, the ones that you guys learn is 32-bit. One of them is the sign. If it's a 0, it's positive. If it's a 1, it's a negative. And then you also have 8 bits for the exponent plus the bias that I'll explain in a bit. the bias from decimal to binary, you gotta add 27, and from binary to decimal, you gotta subtract it. And the rest is basically 23 bits of the fraction bits. That's also called Matisa. So, okay, pay attention to that. So here I have an example from a decimal number to IEEE. Okay, let's see if I can make it make sense. So we have 14.65625. And first of all, there are a couple steps that we have to follow. First, we just convert it to binary, that we always do. We divide this by 2, and then we multiply this by 2, or we follow the 2 by the negative power that we know. After we have this whole number, we gotta write it as a scientific notation, which means we have to move this radical exponent this way, right? Like you make the jump. I don't know, point through it. Like 1, 2, 3, 4, 5, right? So we have right now 1 point and then everything after that, and then a 5. That's exponent. So because it's a positive binary number, we have it equal to 0. And that's it for the sign bit. Now we're gonna find the exponent bits that we have to add the exponent that we found, the 5. We got 127 because it's positive, right? So that's a 132. We have to convert this 132 to binary, which ends up being this. Same way, converting. After we hit the exponent base, we have to find the fraction bits, which are basically the rest after the right exponent of this. These are the fraction bits. So now after we have everything, the sign bit, the exponent, the bias, and the fraction bits, we just combine everything up. We have the sign bit here, 0, because it's positive, the exponent that we found, the 132, and the mantissa, that's the fraction bits. And we just have to add, this is very important, you have to add the extra zeros to make these 23 bits and make the actual representation. Any questions on the steps on this? It's a bit of a process, but once you understand that it's easy to replicate. Okay. Good. So now we have IEEE to decimal. This is a bit faster in my opinion. You have the whole number, right? That you're gonna be given on the test probably, and you have to convert it to decimal. So the first bit, as we know, is a sign bit. So since it's a 1, it means there's a negative. So we just take a note of that. Okay. Then we find exponent bits. That's in the next section. We have to convert this to binary, which we find to be 132. Then the next step, we're just reversing the process. We have to subtract the 127, which we get 5. Now the exponent bits are 5, so that also tells us that we have to take the first 5 bits of the mantissa, which is this, right? The 5 exponent, 1, 2, 3, 4, 5. So this will be the fraction bits for now. So the 1 here, it's implied, okay? You always add this 1, because this is the decimal portion. So we have the negative, we have the negative sign, we have the 1 that we assume before the right exponent, and after this right exponent, we have the mantissa that we found, 5 bits for the exponent. And the exponent moves here, that times 2 to the 5. So after this, we have to move the right exponent and remove it, basically. So we move the point 5 times, 1, 2, 3, 4, 5, and it turns out to be this. Then we change it to decimal with the same method that we had, and we found out that it's negative 16. And negative because of the sign bit. Very important. The sign can really change the answer, right? So, anything to add? Can I continue? Okay. So flip-flops. I think I edited this thing a while ago, right? It hasn't updated. Sorry. So this is better if I have some kind of way of writing, but well, the steps basically are that you have to first check the rising edge of the clock. So every time it goes up, the state of Q is going to change. Okay, every single time. So don't worry about the going down edge. You just rise edge in this case. So the first thing is always a question mark. I cannot write it. Do you mind if I refresh this? Maybe okay. Because I think I say that. Okay, nice. Here it is. So the first one is always in the middle. Why? Because we don't know what happened before. Okay, it will always be a question mark here. Then the next step is to check if the reset is a 1. If it is a 1, it will automatically be a 0. Okay, so we got down a whole cycle. That's until here, the next rising edge, right? So then we check again if it's the 1, the reset, and it's not, so we can continue as normal, okay? But sometimes in the test, they might put like an extra here just to confuse you. Just take that in mind that anytime the reset is up, key will be 0. So after we check the reset and it's no longer a 1, we can go to the enable. If the enable is a 1, we can copy the D to be Q. Okay, for example, here the next clocking right clock edge, we have the enable to be 1, and then we see D, which is a 0. So we basically copy it to, okay, so that's why it's off right now. And then we go forward to the next right edge, we check enable is 1, and then we check D, it's a 1, so we copy it here. Okay, and like that, we just continue. Next clock edge is off. Okay, enable here is 0, so the key is not going to change. So it continues to be 1. So we go to the next right clock edge. Again, it's enable is 0. We're not going to change Q at all the way, because enable is 0. We're just going to continue copying it until this rising clock edge. Don't check. Enable is 1. And in this case, D is also 1, so we copy it again, and that's how it goes all the way to be 1 at the end. Any questions about this? I can say it again, if you guys need me to. Okay, you guys are so smart. Okay. Now, fun stuff. This is the other example that they give on the test sometimes. They have two possible outputs they have to show. Usually the B goes to the L and the C goes to the L2, sorry, L1 and L2. So basically just two problems in one. For this one, you check the reset and the L1 and the A, basically. And so, as always, the first one is always a question mark. Then we continue and we check that the reset is in fact 1. So the same steps. If it's a 1, it's a 0. That does not matter. So we go forward. The L1, we're taking L1 right now, is 0. So we're gonna just copy what we had before. So 0 again. We go forward. The L1 is still off. So we're copying again. Then we go to the next rising clock edge and we find out that the L1 is on. So we're going to check on this one, not that one. Okay, it's a very common mistake that we go forward, but no, we cannot predict. We cannot go to the future. Okay, so we're gonna take the past, and we're gonna copy the D basically. So that's what you do. So here L1 is off. So you just copy what you have. Here is 0, you copy, L1 is still on, so you copy, and then it's off, so you copy what you had. Okay. Now for the next one, for C, it's basically the same. The first one is always a question mark. Then the reset is on, so 0. Then the L2 is on, so you copy and diagonally, see? Okay, now L2 is off, so we copy what we had before. L2 is on again, so we copy diagonally, and it's off, so we copy. Yeah, very straightforward. You just have to remember that you have to check the past, the future, and take an eye on the reset and copy what you had before if L2 or L1 is off. Okay, can I go on? Yeah. Okay, this comes from a homework instruction of homework that I did for this class a couple years ago. So I still have it right there if anyone has a question about it. So here, basically what we're doing is that they usually give you like a text, right? Like a description that you have to follow. So based on that, you can create your own instruction. And at least for me, it's way easier this way. Because right now I know that it's a load store. No, load instruction, sorry. And the instruction said that we want to write, we want to read the filter and write on the T5. And we are also given the values. All of this is given. Okay. So don't forget, all this is given on the instruction. What you have to know is to plug it in, right? So since we're gonna write, right, because it's a load, we have to check T5, and we're given that T5 is in fact 1012 and 452. So we type that in. Then the address of the write is T5, so 5 to binary 101. And because it's a load, we're gonna press a 1 right there. So all this writes enables and read enables are memorization, let's say, but also understanding what the instructions actually do. Okay, so the load, you are gonna take something, right? You have to read something. But in this case, you're also writing certain both things. So that's why we have read enable and write enable both as one. So since we're gonna read from T3 as the instruction says, we have to convert that to binary 0, 1, 1. And oh yeah, I forgot to say that all of these are going to be 0, but the one you're reading to. So D3 will be 1 in this case, and D5 will be 1. It's very dim, but it's a 1. Then the reading data they have, it's here and here, 508. That's on the D3 that we're trying to read. And since we're just reading one register, not two, all these are off or don't cares, and all these are 0. So I think it's a bit different for the test. I think you're actually given like a paragraph of instructions, but it's also good to understand these things. Now this is a R type instruction, I think. I also have an I type, the sub and add. This is a bit different because you have 3 registers instead of 2. So you're actually using the 3 parts of the register file, not only 2. And you need all this on because you're writing, reading, and writing again. So as you know, you read this, then you subtract them, and then you put them on here. If you guys remember how subtraction works. So here's where the subtraction is going on. The RS is subtracting to RP, and it goes to 92. Again, we are writing 2 as given T3, so that's 3 binary. We put that 3 to be 1 and the rest are 0, and it's just the same process. Okay, so we're gonna read from T4, which is 106. This is given, I said before. R2 is also given 14, and the register, yeah. So 100 because it's 4, and then 110 because it's 6 right here. So I know it's a bit fast, but I have more examples right there with my notebook if you guys have any other questions that want to ask me later on. But any questions on register files? Because memory is coming up. Yeah, memory. Basically, 2 types that you guys are gonna learn: RAM and ROM. Right now, just remember that the RAM you can read and write, okay? But on the ROM you can only read. So the RAM will erase once the power is off, and the ROM will stay for a while at least. And it's also very possible to program. And the ones that you're gonna learn are basically these 3 types. The RAM is a raster file, VRAM, SRAM, and for the ROM you got a couple more types. Yep, fun stuff. So this is random access, so this is only read only. And I am aware that this is basically what you guys have to fill out on the test. I remember getting this and it was the memorization. But I think it's easy to find some similarities that I have highlighted for you guys. For example, the 1980, this is like the oldest memory alive, then it's easy to memorize the EEPROM. Then we, yeah, it's like that, it's just memorization, basically. So there are a couple of things that can help you memorize. For example, the large amount of code, like large flash is very large, okay? And also SRAM is something that can be forgotten, like the SRAM can just go on and on and you can forget it. So as I said, EEPROM, 1980s, oldest one alive. EEPROM, now this was reprogrammable and it was also very, very old, but not as old as EEPROM. Now, DRAM can be, what does it say? Large amounts of data, but it can also analyze to uncover patterns. Okay, all these little keywords that you have to remember for the test. Also the ROM, the mask program, I remember it was from a manufacturer, so it's very, very important. And it cannot be changed because, well, it's wrong. Right, it was programmed by a manufacturer and that was it. You could not change it. The register file, you basically store data in the local memory. And also another keyword, packet reviews to the data every day. So, important stuff. Now, OT prompt, it's also manufacturer, but this is small quantities. Okay, not like the mass program, because this is like many things at once, and OT prompt is very small quantities. So, something you gotta remember, some keywords that you have to memorize basically for the test, but that will be it. I don't think you're gonna need it. So, yeah, I guess just practice. I have a couple of other examples on this. I think I have 3. This is one. So if you guys want to know more about it, because they randomize it, right, for exams and stuff. So a couple of keywords for each of the memories will be helpful to memorize. And I think that's all I have. Sure.
So on the previous slide,
Go ahead.
it said that Flash was wrong.
Yeah.
But I thought Flash was it was erasable. So I don't know if that's confusing me. If it's wrong or if it's random.
Fair question. Can you look it up?
Yeah.
Yeah, I think you made it right. It's been a while. But yeah, because Flash it can be erased, but it can be read too, right? Can you write on Flash?
It can be,
You know, it can be programmed.
yeah.
You see, that's what I have it there. Like, it's programmable, but
The AI is saying yes, but then the website says no.
Oh.
So I don't know.
you see, like, I guess you're gonna have to ask the professor because I know there are a couple of different kinds of Flash as well.
Okay.
So I guess the one that we're learning is for programmable, but make sure with the professor, okay? But that's all I have. I have some practice problems on my desk right there. I have a tutor here, and I don't know if I think I'm the last one, right?
Trees
Oh,
are short hairs.
that's it, guys. I'll stay here until 2. Do you guys have any specific questions about the review? Sorry. You guys learned something. Okay.
Thank y'all for whoever's in the Teams meeting. That's pretty much it. I'll stop the recording here and I'll post it. And y'all will be able to see it later today or tomorrow in the
Yeah, I
IEEE
just started
Discord.
learning.
All right, sorry,
Yeah.
Discord or
I
YouTube.
started this morning for
Yeah.
30 minutes.
I tell myself, oh, it's gonna be fine. I
Uh-huh.
think it will be.
Hello everyone, I'll
be covering over the missing parts from the second exam review. It'll be over representation of numbers, signed magnitude, ones and twos complement, binary multiplication, shifters, radix point, and converting fractions from decimal to binary in 2 different ways. So let's start off with the representation of numbers, signed magnitude. So signed magnitude is just a very simple way of expressing negative counterparts. So you just have generally your magnitude, which is represented by your binary representation of the number, and then your sign. So this could be 1 or 0 depending on if it's positive or negative. So if it's negative, you're going to have a 1 as your bit for the sign. So here, for example, -7, your binary representation of 7 is 1, 1, 1. And then because it's negative, you're just going to add a 1 in front of it. And we have just 2 different representations for zeros. You have your positive 0 and you have your negative 0. But one major drawback of sign magnitude is that even though we can express these numbers in a different way, a very simple way, you will have to convert them like in a different manner for arithmetic purposes. Now, ones and twos complement. One's complement is extremely simple. It's just bitwise inversion, where the negative counterpart of a number is just all of its bits flipped. So for instance, 7, its normal binary positive representation is 0, 1, 1, 1. One's complement would switch out all the zeros for ones and all the ones for zeros, as shown here. And generally, a positive number and it plus its negative counterpart will always result in 1, 1, 1, 1 for one's complement. And that means that you have 2 representation of zeros for one's complement, which is not a very ideal case. And that's why we have two's complement, where a positive number plus its negative counterpart will only result in 1 representation of a 0. And that's essentially just taking the bitwise inversion of that number and adding 1. So for instance, for one's complement, you have 1, 0, 0, 0 for the one's complement, the -7. But for two's complement, that would just be 1, 0, 0, 1, because you're adding 1 to the bitwise inversion. Now, another really minute detail about this arithmetic is something known as sign extending. So for positive representation, you can always add zeros in front of it. So for instance, with the 7, for the one's complement example, you can add as many zeros in front of it to sort of facilitate arithmetic processes. But for negative representations, instead of having leading zeros, you'll have leading ones instead. And now I'm going to be going over binary multiplication, which is really straightforward. But again, I encourage you guys to really go through the steps and write it down to avoid any minor mistakes. The steps for this is just generally converting the decimal numbers into their binary representations. And then you multiply both of these binary representations, and remembering that the intermediate sum is where you're adding all those different bits together. So 0 plus 0 will equal 0, 0 plus 1 will equal 1, and 1 plus 1 will equal 10. So for 12 times 15, you're going to convert it to its respective binary representations. For 12, it will be 1100, and for 15, it'll be 1111. And basically over here, you're going to multiply normally, and then you're going to find the product of it by their intermediate sums, and every time ensuring that there's a shift. And your resulting product for 12 times 15 should be 10110100. And again, you can try this out on your own and check to see if your answer is correct. But there is there's a shortcut to this problem as well, which is known as shifters. So remember, when multiplying these 2 binary numbers, the original number, which is the top number, in this case would be 1100, reappears several times in the intermediate sums. You can see it reappears 1, 2, 3, 4 times, as highlighted in yellow. And the amount of shifting is determined by a number of ones in the second value that is being multiplied. So in this case, the second value is 1111. And there is 4 different ones. So you're expecting 4 different representations of 1, 1, 0, 0 in your intermediate sum. And you're doing maximum 3 shifts as shown by sort of like the number of ones in the second value. And it's place. So 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. And then you will have 3 shifts. So shift and add is just a simpler method of doing binary multiplication. Now, radix point, this is also a very easy topic. It's if you can think about it as like the decimal point of binary. So everything left of the radix point will be 2 to the power 0 onwards. So just all the positive twos, powers of twos, and everything to the right of the radix point will be all the negative powers of twos. So this sort of radix point, it opens up possibilities of fractions in binary, but the only limitation that really exists is that the decimal can only be powers of 2. So if you're converting from, say, like a decimal of 0.1 to binary, you can get really, really close to the number, but you won't get it exactly because 0.1 is just not a power of 2. So an easier example would be the decimal value of 0.5 being converted to binary. Since 2 to the power of -1 is a power of 2, you would represent 0.5 as 0.1 in binary. Now, the last thing I'll be covering over in this video is converting fractions from decimal to binary. So negative binary fraction, it's basically you're converting decimal to binary, you flip all the bits, bitwise inversion, and add 1 to the least significant bit. I don't think you're going to have this a lot in the exam, but it's good to remember. It's just a very minute detail. For just converting fractions in general from decimal to binary, there's 2 methods to do it, subtraction method and multiplication method. Personally, the multiplication method is really simple, but I'll go over both methods. So for the subtraction method, first you ignore the fraction part and focus on the left-hand side. So for this, you're going to focus. So we're trying to convert 2.625 into binary. We'll focus on the non-fraction part, which is 2, and that converted in binary will equal to 1. Next, you look at the powers of 2 after the radix point and keep subtracting the highest possible values. Places 1s at the respective places after the radix point. So essentially what that means is that I'm going to take the 0.625 here, and the first possible value I could subtract from 0.625 is 0.5. And once I subtract that, I get 0.125. The next possible number that I could subtract 0.125 with is 0.125. Again, I'm skipping over 0.25 because it's too big. And that's just a subtraction method where you consistently, whatever sort of negative power of 2 I'm subtracting from the initial decimal is where the respective ones will be placed. The only disadvantage with this is the fact that you must know the negative powers of 2. And of course, if you write this down, it'll be easier for you to do this way. But another way of doing this is the multiplication method. So the first step is, again, you ignore the fraction part and you only focus on the non-fraction part, which in this case is 2, and that in binary will be 1. Next, what you'll do is that you're going to take the fraction portion of the decimal and keep multiplying it by 2. And if it's greater than 1, say over here, I take 0.625, I times it by 2, I get 1.25. So I look at the whole number, in this case, 1. And my next step is that once it's greater than 1, I discard the 1 and focus on the fraction part again. And I keep repeating step 2. So what that means is, like I mentioned before, 0.625 times 2 will give me 1.25. So for that decimal place, I'm going to put a 1. And then I'm going to discard the 1, and then I'm going to be left with 0.25. And I'm going to multiply that by 2 again, and I'll get 0.5. And since it's not greater than 1, I'm going to put a 0 in that respective place. And then I'll take 0.5 times 2, I get 1.0. And then since it's equal to or greater than 1, I'll place a 1 there. And once I discard the 1, I'll just be left with 0. So that's when you know your conversion is completely finished at that point. Okay, that should be the end of this video. I hope this helps.